In this lecture, we will introduce a technique called Poisson Approximation to analyze the balls and beans model. And after that, we will show two example applications of this new technique. The first one is about the analysis of the lower bound for maximum load. And the second example is to revisit the coupon collectors problem. Let's start. So suppose that we are going to throw n balls into n bins independently and uniformly at random. So this is the standard balls and bins model. From our previous discussion, the number of balls in a particular bin, it turns out that it is very similar to a Poisson random variable with parameter m over n. But then let us ask a higher level question. How about the distribution of balls in all the n bins? So we are not focusing on just one particular bin, but then we are going to look at all the bins at the same time. So one simple idea is to think of the number of balls in all these n bins. Each of them is an independent Poisson random variable. However, this idea is not exactly the same as what can actually happen. It is because in the actual scenario, the number of balls in all the n bins is always m in total. But on the other hand, if we are assuming that each bin is an independent Poisson random variable, then the sum of these n random variables could be anything. It could even be 0. So we have two different scenarios. One is the actual case that is happening, where we are throwing exactly n balls. The other case is we treat each of the bin as an independent random variable. These two are very different, but somehow, interestingly, they are highly related. So we will call the first case where we are throwing exactly m balls into n bins, we will call it the exact case. To help us to memorize it easily, we use the variable x to represent the number of balls in each bin. So x1 is the number of balls in the first bin, x2 is in the second bin, and so on and so forth. So x has a sound like exact. On the other hand, when we are trying to represent each bin by using an independent Poisson random variable, we will call this the Poisson case. So here we are going to define the random variables y1, y2, y3 up to yn, such that y1 represents the number of balls in the first bin, y2 the number of balls in the second bin, and so on and so forth in the Poisson case. So in the Poisson case, we will assume that for each of the bin, the average number of balls is m over n. So in that case, yi for each I will be a Poisson random variable with parameter m over n. So the notation little m here in the random variable here indicates the total number of balls in the exact case or the expected total number of balls in the Poisson case. So why are these two scenarios related? So this is the theorem. Suppose that somebody tells us that the total number of balls thrown in the Poisson case is equal to k. Now under this condition, the distribution of y1, y2, y3 up to yn will be the same as the distribution of x1, x2, x3 up to xn. But for the x cases, here we assume that we are going to throw exactly k balls. So we have a little parameter k here, as can be seen. But on the other hand, for the Poisson case, the parameter here is the same as before, is m, except that in the Poisson case, we are given the condition that the summation of all the yj values is equal to k. Now this theorem holds regardless of what is the value of m and what is the value of k. So we will see why this is true as follows. So we are going to show that the distribution here under the condition of this one is the same as the distribution here by knowing that we are throwing exactly k balls in the exact case. So the proof is actually very simple. We are going to prove this by direct method. Okay. So suppose that k1, k2 up to kn represents a certain distribution of k balls. So the summation of these k values, so these little k values, is exactly equal to big K here. And then each of these values are non-negative, integer. Now for the exact case, the chance for the distribution of balls is exactly the same as k1, k2 up to kn will be equal to k factorial divided by k1 factorial, k2 factorial up to kn factorial multiplied by 1 over n to the power k. So this term is actually, we have k balls, right? We need to select exactly k1 balls to put into the first bin, and then exactly k2 balls to put into the second bin, and so on and so forth. So this term represents the number of ways to do such a selection. And for each particular selection, it occurs with probability 1 over n to the power k, because for the first ball that we need to put it into the first bin, there will be 1 over n chance. For the second ball to be put into the first bin, there will be 1 over n chance, and so on and so forth. So for each ball that we want to put it into the desired bin, then it occurs with probability 1 over n. So in combination, in summary, the chance for a particular scenario that happens is 1 over n to the power k. And then there are so many different scenarios that will yield the same distribution. So this is the probability for the exact case. And now let us analyze the probability of the same distribution in the Poisson case. But this time, we are conditioned under the condition that the summation of all the yi values is equal to k. So for this one, this is equal to, so if you look at it, this is probability of a certain event given another event. So probability of E given F. So probability of E given F is equal to probability of E and F divided by probability of F. So the denominator here is exactly the probability of this one. But for the numerator, the probability of E and F, when E happens here, we are actually claiming that the right-hand side, this F must happen. It is because this is a certain distribution of k balls. So when this happens, automatically F will happen. So the numerator can be simplified to be something like this, just probability of E. Okay, now let us further simplify this fraction. Now notice that for the bottom part, the summation of all the yj values, so this is summation of independent Poisson. It turns out that it is a Poisson, okay? And then for the first part, it is for independent and independent Poisson to have the corresponding values of k1, k2 up to kn. So actually, these two terms, the numerator and the denominator, can be easily calculated. So the numerator will be the product of the chance of yj equals to kj, because they are all independent. And for the bottom part, it is just the chance for a certain Poisson random variable with parameter m, because it is the sum of n Poisson with parameter m over n. So this becomes a Poisson with parameter m, such that this Poisson random variable will admit the value of k. So the bottom part is just e to the power minus m multiplied by m to the power k divided by k factorial. Now, for the numerator, it is expanded. Okay, so we are actually replacing this term by the definition, so this term. So as we can see, there are n terms of e to the power minus m over n multiplying together. So this will eventually cancel with this e to the power minus m. And similarly, there are m to the power kj terms, and when they are multiplying to each other, we get m to the power k. So the m to the power k terms will be gone. So what is left will be, there will be n to the power k left, there will be kj factorial left, and there will be k factorial left. So after simplification, we will get exactly the same bound as we see here. So we have now proven the theorem to be correct. So what does that mean? So here, although that the Poisson case is not the same as the exact case, but the conditioned Poisson case is going to be the same as the exact case. So conditioned Poisson is equal to exact. Okay, now we have this key theorem, and then we are going to utilize this key theorem to give more important result. So here, suppose that Z is a non-negative random variable that is based on the distribution of balls. So examples, for instance, the maximum load. So maximum load is always non-negative, and it is based on the distribution of balls. If I know the distribution, then I can tell what is the number of balls in the photo spin, so I know what is the maximum load. So maximum load is a random variable, which is non-negative and depends on the distribution of balls. And similarly, number of empty bins is also an example, or any indicator of a certain scenario that is based on the distribution of balls. So for instance, whether there are any empty bins, or whether the maximum load is greater than or equal to 5, something like this. So this is going to be an indicator. When it happens, it has value 1, and when it doesn't happen, it has value 0. So such an indicator is also a random variable, and then it depends on the distribution of balls. Now, in the next result, we are going to show that we can utilize the previous theorem so that we can give relationship of the expected value of this kind of random variable Z in the two different scenarios. But before we do the interesting result, let us first introduce a simple bound on n factorial. Okay. So we claim that n factorial is less than or equal to e square root n multiplied by n over e to the power n. So the proof is based on calculus. So first of all, we notice that log of n is a concave function as n increases. So in that case, if we are going to integrate from j minus 1 to j for this function log x dx, assuming that j is a positive number greater than or equal to 1, okay, then in that case, we will see that the area under the curve will be greater than or equal to, this is concave, greater than or equal to log j minus 1 plus log j divided by 2. So this is actually the trapezium that is defined under the curve here. So we will see that this is true. So if we sum everything up, instead from j minus 1 to j, this time from 1 to n, then in that case, we will see that we are going to add up what? Add up log 1 plus log 2 divided by 2, log 2 plus log 3 divided by 2, and so on and so forth, up to log n minus 1 plus log n divided by 2. So after doing terms collection, we will find that we will have one copy of log 2, one copy of log 3, one copy of log everything up until log of n minus 1, and half a copy of log 1, which is 0, and then half a copy of log of n. So after collecting terms and simplifying, so this is actually log of n factorial minus log of n divided by 2. On the other hand, when we do this integration, we will find that this value is exactly equal to this one. So we will have n log n minus n plus 1 is greater than or equal to log of n factorial minus log of n over 2. Now when we take exponentiation on both sides, we will immediately get this lemma. So we are done. So I will leave this for you as an exercise. This is very simple. Okay. Okay, once we have this bound, we are ready to show this theorem. So here, suppose that Z is a certain random variable. So this is a certain function that depends on the distribution of balls x1, x2 up to xn. Then we claim that the expected value of this Z in the exact case is related to the expected value of Z in the Poisson case in the following relationship. So E multiplied by square root of the number of balls multiplied by expected value of Z in the Poisson case is greater than or equal to the expected value of Z in the exact case. So how do we prove this theorem? Okay, so we start from expected value of Z in the Poisson case because it is easier to analyze. Okay, so the expected value of Z in the Poisson case by using the conditional expectation formula. So this is going to be the conditional expectation, the summation of the conditional expectation, each of them weighted by the corresponding probability that it occurs. So here, this weight is, so how do we divide the cases? So we divide the cases based on the total number of balls in the scenario. So there are different values of k that we can have. K could be equal to 0, 1, 2, 3 up to infinity. So based on the number of balls in total, so we have the conditional expectation for each case, and then it is multiplied by the corresponding probability that it occurs. Now notice that this function f, or this random variable, is non-negative. So the conditional expected value for each of the case is also non-negative. So when we are summing up all the different k for this term, then we are summing a lot of non-negative terms. So in particular, this should be greater than, okay. So in that case, this will be greater than, so this is a greater than or equal to symbol. So let me write it down, or greater symbol. Then when we just focus on one particular case, let's make it greater than or equal to, to be safe, okay. Okay, so give me a change here. When we consider just one particular case where we set this k to be m here, okay. And now, what do we know? This probability occurs with this value. So this is the definition of a Poisson random variable with parameter m, right? And then for this part, this is the conditioned Poisson. So conditioned Poisson is equal to exact. So we can replace this by the expected value of the random variable in the exact case. And by using our previous bound on n factorial, so this time n factorial here, we can simplify this term into e square root m. So after doing the simplification, this is actually another mistake. Okay, so this should be greater than or equal to. Then we are done. It is because by translating this term to the left-hand side, we will have e square root m multiplied by e of the random variable in the Poisson case greater than or equal to e of the random variable in the exact case. Okay, so this is what we can do. And finally, okay, so this is a special case of the previous relationship. So suppose that this time we have everything the same as before. Z is a random variable based on the distribution of balls. But suppose that we also know that the expected value of this random variable in the exact case is monotone in M. So what is meant by monotone in M? So as M increases, this expected value is always increasing. Or as M increases, this expected value is always decreasing. So in this case, this is monotone. So examples like maximum load. So the expected value of this maximum load is monotone in M, because as M increases, we will expect the number of balls in the Fuller spin will also increases. So in such a case, as M increases, the expected value increases, so this is monotone. And also another example, the number of empty bins. So expected of number of empty bins is also monotone in M, because as M increases, there will be fewer chance to see an empty bin, because we are putting more and more balls into the bins. So in that case, we will expect to see fewer and fewer empty bins. So expected number of empty bins will decrease as M increases. So these are the examples where the expected value is monotone. Now, when the expected value is monotone, now we can replace this term e square root m by the term 2, so that what? So that we are going to make these two expected values to be closer to each other, the bound to be closer to each other. Now, the purpose of having this relationship is very good. It is because the expected value in the exact case, because of the dependency of balls, is difficult to analyze. On the other hand, the expected value of the Poisson case is much easier to analyze. So when this expected value is going to be small, in particular, when we are talking about indicators, when this is going to be small, then multiplying by 2 is still small. So in that case, we will see that this is still small. So this is how one may apply this theorem to give us some interesting results. So this is the end of the first part.